Here is a combined summary of the two pages. Perm is a parametric representation for 3D human hair modeling, designed to facilitate various hair-related applications. Unlike previous work that jointly models global hair shape and local strand details, Perm disentangles these two aspects using a PCA-based strand representation in the frequency domain. This approach allows for more precise editing and output control. The model is formulated as M, theta, beta, R, where the output hair is conditioned on the guide strand parameter theta for its global shape, the hair styling parameter beta for its local details, and a predefined root set R for the hair density. Perm's strand representation fits and decomposes hair geometry textures into low to high frequency hair structures, which are later parameterized with different generative models. These models emulate common stages in the hair modeling process, such as guide strand authoring, residual texture modeling, and guide interpolation. The learned principal components form an explainable space for hair decomposition, where initial components capture low-frequency information and subsequent components encode high-frequency details. The Perm model is trained to serve as a generic prior for various hair-related applications, including 3D hair parameterization, hairstyle interpolation, single-view hair reconstruction, and hair-conditioned image generation. Experimental results demonstrate Perm's capability across multiple applications, achieving performance equivalent or superior to state-of-the-art task-specific alternatives. A novel application of using Perm-generated hair for conditional image generation is also introduced. The authors also review existing literature on geometric and volumetric hair modeling, highlighting the limitations of previous approaches and the need for a parametric model that can disentangle global hair shape and local strand details. This research paper introduces Perm, a parametric representation for multi-style 3D hair modeling. Unlike existing approaches that rely on volumetric fields or single hair texture maps, Perm represents hair strands with multiple frequency components, enabling independent control over global hair shape and local strand details. The Perm model is composed of several components, including a guide strand function, a super resolution function, and a hair styling function. These functions take parameters theta, beta, and gamma, which are used to synthesize guide textures, upsample them, and generate residual textures. The resulting geometry texture is then sampled and decoded to obtain the strand geometry. The paper highlights the limitations of existing hair modeling approaches, including their inability to capture curly and kinky hair. It also discusses the benefits of using a frequency-based representation, which allows for a more compact latent space and improved preservation of strand curvatures. The Perm model is formulated as a hybrid hierarchical parametric hair representation, incorporating both linear and nonlinear parameterizations across different hairstyles. The paper demonstrates the effectiveness of this approach through various experiments, including smoothing hairstyles by truncating strand PCA coefficients and creating diverse composite hairstyles by blending low-rank and high-rank PCA coefficients from different hairstyles. The strand parameterization is achieved through a low-dimensional parameter space based on PCA in the frequency domain. This approach is inspired by the nearly periodic behavior of hair strands and allows for a more efficient representation of hair geometries. The paper also compares its approach to existing methods, including VAE-based modeling, and highlights the benefits of its frequency-based formulation, including improved preservation of strand curvatures and reduced training time and GPU memory consumption. The research paper discusses a novel parametric representation for multi-style 3D hair modeling, focusing on strand geometry and hairstyle parameterization. It introduces a PCA-based strand parameterization, enabling the decomposition of strand geometry into a meaningful parameter space. This allows for the creation of diverse hairstyles by blending low-rank and high-rank PCA coefficients from different hairstyles. The paper also proposes a texture-based representation for 3D hair, where guide strands are synthesized using a neural network. The guide interpolation process is formulated as an image super-resolution problem, and the paper presents experiments and results on various aspects, including strand representation, guide strand synthesis, and guide interpolation. The results demonstrate the effectiveness of the proposed methods in capturing the rough shape and high-frequency details of hair strands, as well as in synthesizing and interpolating guide strands. Here is a combined summary of pages 7 and 8 of the research paper. The authors present a parametric representation for multi-style 3D hair modeling, dubbed Perm. They compare their PCA-based strand representation with VAE-based representations and a simpler PCA-based formulation in the spatial domain. The results show that their method achieves the most natural results, resembling the shape of guide strands and forming reasonable hair partitions. In the hair styling module, the authors employ a VAE architecture to reconstruct sharper residual textures, trading some sampling diversity for higher reconstruction fidelity. They compare their method with Groom Gen, a previous work that learns hierarchical representations of 3D hair. The quantitative comparison indicates that their representation achieves significantly better reconstruction with slightly higher curvature errors. The authors demonstrate various applications of Perm, including 3D hair parameterization, hairstyle interpolation, single-view hair reconstruction, and hair-conditioned image generation. In 3D hair parameterization, they fit Perm parameters to target 3D hair models through differentiable optimization. In hairstyle interpolation, they introduce separate parameters to control global hair shape and local strand details, allowing for editing hairstyles with varying granularity. In single-view hair reconstruction, they optimize Perm parameters to minimize the energy of generated hair when projected to 2D images. The results show that their method excels in reconstructing the global shape of the reference hairstyle and preserves local details better compared to hairstep. Finally, they demonstrate the use of Perm in facilitating conditional image generation, where they sample and edit hairstyles in 3D and feed the extracted hair geometry to text-to-image models to generate the final images. The authors acknowledge limitations of their model, including challenges with intricate styles like buns and braids, and propose future work directions, such as developing a systematic framework to capture a diverse set of real data and exploring controllable 3D hair synthesis with multimodal input signals. The research focuses on developing a parametric representation for multi-style 3D hair modeling, aiming to improve the accuracy and efficiency of hair modeling from a single image. The authors introduce Perm, a novel parametric model that can fit a wide range of hairstyles. This is achieved through a subset of 3D hair models fitted by Perm, showcasing its versatility. The methodology involves interpolating different parameters to generate various hairstyles, ensuring a smooth transition between styles. The authors also compare their approach with existing methods, highlighting the superiority of Perm in terms of accuracy and flexibility. The paper concludes by discussing future work, including the integration of Perm with other facial modeling techniques for more comprehensive character creation. Here is a combined summary of pages 11 and 12. This research paper provides a comprehensive review of parametric representations for multi-style 3D hair modeling. The authors cite various works on hair geometry capture from multiple images, expressive body capture, and styled GAN encoders for image-to-image translation. They also reference studies on embodied hands, U-net convolutional networks for biomedical image segmentation, and neural strands for learning hair geometry and appearance. The paper highlights the importance of 3D hair synthesis using volumetric variational autoencoders, CT2 hair for high-fidelity 3D hair modeling, and deep sketch hair for deep sketch-based 3D hair modeling. It also mentions neural haircut, a prior guided strand-based hair reconstruction method, and HAR, a text-conditioned generative model of 3D strand-based human hairstyles. The authors discuss various approaches to hair reconstruction, including doctor hair, which reconstructs scalp-connected hair strands without pre-training via differentiable rendering of line segments. They also cite works on example-based hair geometry synthesis, local appearance models for volumetric capture of diverse hairstyles, and Noi wigs, a neural dynamic model for volumetric hair capture and animation. Furthermore, the paper references other studies on hair modeling, including HVH, a hybrid neural volumetric representation for dynamic hair performance capture, and Mono hair, which models high-fidelity hair from a monocular video. The authors also mention Neural HD hair, an automatic high-fidelity hair modeling method from a single image using implicit neural representations. Overall, this paper provides a thorough review of existing methods and approaches in 3D hair modeling, highlighting the complexity and challenges of this task, and discussing various techniques and algorithms that have been proposed to tackle it.